Chapter 14, the ideal gas law and kinetic theory. So in chapters 12 and 13, we introduced the idea of temperature and heat transfer, but we focused on solids and liquids. We didn't get to apply that to gases. Now in chapter 14, we're introducing gases into the mix, if you will. So we first need to study gases a bit, and then in chapter 15, we'll get to study things like heat involved with gases, as well as work, which makes up what's known as the field of thermodynamics. But first, we need to understand a little bit more about gases. So this is where we get into a bit of chemistry terms. If you've taken chemistry at this point, this will be much more familiar to you. If you haven't, that's okay. We're just going to take a little dip into it. And if you ever do take chemistry, it'll be that much more familiar. So our very first section is looking at molecular mass, the mole, and Avogadro's number. So atoms, it turns out, are really, really tiny. So if we stuck with our standard kilogram of mass, we'd be dealing with really, really small numbers, and it'd be hard to compare them to each other. So to make that easier, a mass scale known as the atomic mass scale was introduced. A very, very small scale that will help with comparing relative masses. The unit is called the atomic mass unit, and it has the symbol U to abbreviate it. The reference element that's chosen is the most abundant isotope of carbon, which is carbon-12. So the atomic mass unit was defined based on carbon-12. It said that carbon-12 is exactly 12U. What is a U? Well, a U, it turns out, is a tiny, tiny fraction of a kilogram. Here we have the conversion factor, right? One atomic mass unit is 1.6605 times 10 to the negative 27 kilograms. Whew, that is tiny. And that's because atoms are tiny. So this sort of information is packed into a periodic table, where on the periodic table, we have the elements and they're, right, H for hydrogen, Li for lithium, so on and so forth. And there's the atomic number that tells you about the atoms, and then there's the atomic mass. And the atomic mass is given in atomic mass units. So a lithium atom, Li, has a mass of 6.941 U. The periodic table just usually leaves those units off. But what it's actually telling you is the mass. And now you know, if you didn't already. Now, another common way to describe molecules and atoms is dealing with something known as the mole. And this is not an earthbound creature. This is another unit, if you will. It's another method of counting. So 1 mole of a substance contains as many particles as there are atoms in 12 grams of the isotope carbon-12. There we have it, another definition based upon carbon-12. So the number of atoms per mole is known as Avogadro's number. I always thought when I was learning this that it was avocado's number, but it's Avogadro's. And we abbreviate in physics with N sub A. And Avogadro's number then is 6.022 times 10 to the positive 23 inverse moles, right? So this is 1 over moles. And Avogadro's number allows us to go from a number of atoms or number of particles into a number of moles. And that's shown with this equation here. This is a handy relationship, right? Where if you have a number of atoms, you divide by Avogadro's number, implicit in the numerator of Avogadro's number is that it's atoms or particles or some sort of number of things per mole. So when you divide the number of things by a number of things per mole, the number of things, the atoms, if you will, cancel out, and all you're left with is 1 over inverse moles. Or in other words, you get moles. So we use little n to represent the number of moles and capital N to represent the number of atoms. This is an important distinction because we'll be using both in this chapter. So make sure that you write your N's distinctly so you can distinguish between number of moles and number of atoms. Right? Taking this a little further, if we look at that definition of the number of moles, that's the number of atoms divided by Avogadro's number, and if we multiply it by the mass of the particle divided by the mass of the particle, which is just multiplying by 1, so that's not actually changing anything. Well, if we have the mass of a particle times some number of particles, that's just going to be the total mass, m, of the substance. If we have the mass of the particle times Avogadro's number, that will give us something known as the mass per mole. So the mass per mole is going to be in units of grams per mole. And it has the same numerical value as the atomic or molecular mass of the substance in atomic mass units. So you can think of it as the same as the atomic mass. So hydrogen has an atomic mass of 1.00794 grams per mole, while the mass of a single hydrogen atom is 1.00794 U. So these are very similar. And what you may be noticing is that periodic tables come in handy. So periodic tables aren't something you have to memorize in physics class. They're something that's provided for you. There's one here in the slides if you want as a reference. There's also one on the inside back cover of your textbook. So either one of those work. On an exam, you'd either be given the information in the problem statement or as a periodic table as another reference. So here's one that's pretty good, right? And we have, again, the weight is shown, and that is the atomic mass. So that can be in U or in grams per mole. All right, let's try an example with this. And might as well do it with diamonds, right? Girl's best friend. So the Hope Diamond and the Rosser-Reeves Ruby. The Hope Diamond is 44.5 carats, is almost pure carbon. The Rosser-Reeves Ruby, 138 carats, is primarily aluminum oxide, Al2O3. 1 carat is equivalent to a mass of 0.200 grams. Determine A, the number of carbon atoms in the Hope Diamond, and B, the number of aluminum oxide molecules in the ruby. All right, so this is really interesting, working with carats, right? That's a unit we haven't seen much before, but they give us a clue about it. They say that a carat is equivalent to a mass of 0.2 grams. So that means this is really just telling us the mass, and then we'll just need to convert it to be in units of grams. And it's okay to work with grams in this chapter when, with these relationships, because our molar mass is in grams per mole. All right, so we have the mass of each of these. Do we have any other information? The other key information here is that it tells us the diamond is almost pure carbon, which we know is C, and then the ruby is aluminum oxide. And they give us the formula for it, which is something you wouldn't be expected to know, that aluminum oxide is Al2O3, because this isn't a chemistry class. But if you're given this formula, this molecular structure Al2O3, from that you can figure out the mass. Right? And to do that, that's where we have to go back to the periodic table. So let's take a look at our periodic table, and notice we have carbon, and so that gives us the that it's 12.011 grams per mole. For U, right? And then for aluminum oxide, we're going to need the oxygen, O, as well as the aluminum, Al. So we'll take the 26.98 and the 15.999, but we're going to need to multiply them by however much we have of each. So I think let's double check. Yeah, aluminum 2, oxygen 3. So that means the oxygen is going to have to be multiplied by 3, and the aluminum will have to be multiplied by 2, because there's 2 aluminum atoms there. So we have to account for both of them. With this in mind, if we know the grams per mole, and we know the grams, that tells us that we can then get to a number of moles, right? So this is our mass, which we can convert into units of grams. And then we know, say, carbon is 12.011 grams per mole. So mass divided by our mass per mole will get us number of moles, little n. Is that what we're solving for here? Let's see, number of carbon atoms. It doesn't say number of moles. Since it says number of carbon atoms, what it's asking for is capital N. So capital N, we remember, is the number of atoms, and that's related to the number of moles by Avogadro's number. All right, so with this in mind, we're now in good shape to solve the problem. So let's pull this all together into a solution. All right, so the number of moles is equal to the total mass divided by the mass per mole. So for the Hope diamond, we have that it's 44.5 carats times this conversion factor of 0.2 grams per 1 carat. So the carats cancel out and we're left with grams in the numerator. And then we're going to divide by the mass per mole of carbon, which is that 12.011 grams per mole. So now the grams will cancel out, and we're left with 1 over inverse moles, which gives us moles. This is just the number of moles, though. To get it into the number of atoms, we then have to multiply the number of moles by Avogadro's number. So 0.741 moles times 6.022 times 10 to the positive 23 inverse moles. So that comes out to 4.46 times 10 to the 23rd atoms of carbon. Cool. For the ruby, right, the aluminum oxide is a little more complicated as mentioned. We have to take the mass of the 2 aluminum atoms, so 2 times 26.98 U, plus the mass of the 3 oxygen atoms, so 3 times 15.999 U, which comes out to 101.96 U, which is also going to be the same as 101.96 grams per mole. So we will use that as our mass per mole number, and then the mass is just the 138 carats by that conversion factor, which comes out to 0.271 moles. This should be moles. And so then we have 0.271 moles times Avogadro's number, which cancels out the moles, and we're left with 1.63 times 10 to the 23rd atoms. So this helps to highlight how we're going to be able to go back and forth between a mass per mole, between a number of moles, a mass, and a number of atoms. So you want to be familiar with all of these variables. They're very similar, so it's easy to confuse them. So I encourage you to write out on your crib sheet what each of them means, right? So that you're comfortable moving between moles and number of atoms. That's a common one we'll be doing a lot of. All right, so this section introduces it, and we'll see one application of knowing the number of moles and the number of atoms in the next section.